photoelectrons are emitted when 400 nanometer radiation is incident on a surface of work function 1.9 electron volt. These photoelectrons pass through a region containing alpha particles. The maximum energy electron combines with an alpha particle to form a He plus ion, emitting a single photon in this process. He plus ions thus formed are in their fourth excited state. Find the energies in electron volt of the photons lying in the 2 to 4 electron volt range that are likely to be emitted during and after the combination. So for this question, we begin by calculating the value of the incident energy, which is equal to hc by lambda, or we can put over here as 1240 by lambda in nanometer. So the value will be in electron volt. So if we do the necessary calculation, we get 1240 by lambda in nanometer, that is 400. So the value which we obtain is 3.1 electron volt. So this is the value of incident energy on the surface, which is having a work function of 1.9 electron volt. So if this is the value of work function, so I can calculate the kinetic energy maximum of the emitted photoelectron, which is going to be equal to incident energy minus work function, that is 3.1 electron volt minus 1.9 electron volt, and the value we obtain is equal to 1.2 electron volt. So this is the maximum energy of the emitted photoelectrons. Now the question is saying that these photoelectrons pass through a region containing alpha particles. A maximum energy electron combines with an alpha particle to form a He plus ion. So over here I can say that the maximum energy photoelectron combined together with a He2 plus ion and convert it into He plus ion. Now this one is in the fourth excited state, which the question is saying. A photon is emitted. So this is the required reaction which is exactly taking place by the photoelectrons emitted. So over here I am saying the fourth excited state over here is implying that the electron enters n equal to 5. So the electron enters n equal to 5. This is what the meaning of fourth excited state is, and the energy corresponding to the fourth excited state can be calculated as minus 13.6 z square by n square. Now since it is a helium nucleus, so over here I can write it as minus 13.6 into 2 squared by 5 square. So this is the value of the energy of the fourth excited state, which we calculate equivalent to minus 2.18 electron volt. So this is the value of the energy corresponding to the fourth excited state. Now the energy of the emitted photon in the above combination reaction, which the question is asking us. So I can say, therefore, the energy of emitted photon, so this will become equivalent to 1.2 plus 2.18. So it will acquire both these energies, and the value will become equal to 3.4 electron volt. So the energy of the emitted photon in the above combination can attain a value of 3.4 electron volt. Now we are looking after the possibilities that can take place after the recombination reaction. Now after the recombination reaction, electron may undergo transition from a higher level to a lower level, thereby emitting photons. So we are calculating energy corresponding to n equal to 4, n equal to 3 and n equal to 2. So if we do so, we can calculate that E4 is equal to minus 13.6 into 2 square by 4 square, and we obtain this is equal to minus 3.4 electron volt. Energy corresponding to n equal to 3 can be calculated as minus 13.6 2 squared by 3 square, and the value is equal to minus 6.04 electron volt. And then we are calculating energy equivalent to E2, which is equal to minus 13.6 into z square by n square, and the value is equivalent to minus 13.6 electron volt. So now there are possible transitions which can take place. So now we are calculating the energy corresponding to the possible transitions. We are asked to calculate the energy transition that is taking place or lying between 2 to 4 electron volt range. So 2 to 4 electron volt range is asked. That is the reason why we are not calculating energy corresponding to ground state or E equal to 1. So the first possible transition which we discuss over here is the transition between n equal to 5 to n equal to 4. N equals 5 to n equal to 4. So the value corresponding to this transition can be calculated as delta E is equal to minus 2.18 minus of minus 3.4, and on subtracting we obtain it as equal to 1.28 electron volt. So the value corresponding to n equal to 5, that is this value, and corresponding to n equal to 4, which is this value. So if we subtract these two's magnitude, we will obtain 1.28 electron volt. Now the next one which we are finding is the transition that is taking place from n equal to 5 to n equal to 3. So now the energy corresponding to n equal to 5 to n equal to 3. So n equal to 5 is having a value of 2.18 electron volt, and n equal to 3 is 6.04 electron volt. So if I subtract these two quantities, we obtain a value of 3.84 electron volt. So the energy corresponding to transition from n equal to 5 to n equal to 3 is 3.84 electron volt. Next, we are looking for transition from n equal to 5 to n equal to 2. So n equal to 5 and n equal to 2 will give us a value equivalent to that is 13.6 minus 2.18, that is 11.4 electron volt. And the next one which we are discussing is the transition from n equal to 4 to n equal to 3. So n equal to 4 to n equal to 3, the value of energy difference is coming out to be 2.64 electron volt. Now since the photons that are likely to be in the range of 2 electron volt to 4 electron volt, so we are identifying between 2 to 4 electron volt. The values corresponding are 2.64 electron volt, 3.84 electron volt, and the value which we initially calculated, that is 3.4 electron volt. So these are the possible values of energy of the photon emitted. So therefore energy of photon that is lying between 2 electron volt to 4 electron volt can have the following values: 2.64 electron volt, 3.4 electron volt, and 3.84 electron volt. So this is going to be our answer for question number 2.